Good morning. Today, in the global webinar on sustainable and earthquake resilient structure, I will present the topic about the self-centering energy dissipation systems for earthquake resistant structure to enhance the seismic resilience of a community. Contents of the presentation will be brief introduction about the self-centering system, and then I will discuss two main self-centering dissipation systems that I have developed, which is self-centering viscous damper cable system and self-centering box slit damper. Main objective of self-centering seismic damper is to dissipate the energy and simultaneously provide the self-centering capability to the structure and the damper in order to reduce the lateral residual drift in the structure after the severe earthquake event. In this regard, the self-centering devices usually use the conventional dampers like friction damper, metallic yielding damper, viscoelastic damper, or viscous damper, or other conventional dampers, and combine it with the recentering ability, which is mostly provided with the pre-stressed tendons, different kind of springs, or advanced materials like shape memory alloy, which provides a super elastic property for the recentering of the damper. Hence, they also provide the enhanced post-yield stiffness of the conventional dampers, and they are able to reduce the residual drift in the structure in case of an earthquake. A self-centering damper retrofitted structure, when appropriately designed, can almost eliminate the deformation-related damages. This residual deformation can be source of some problems like collapse due to aftershocks or severe damage to the main structural component. Self-centering systems can reduce or eliminate the need to repair and replacement, which can save time and cost. They can enhance the dissipation capacity and post-yield stiffness of the conventional dampers. However, most of the self-centering systems are relatively new technologies, though they are practical and research have shown their effectiveness, but still there are no proper guidelines for designing such systems, and they can be expensive compared to the conventional dampers. First, we will talk about the self-centering viscous damper cable system. Viscous damper cable system is a unique self-centering system developed to seismically retrofit the low to mid-rise steel structure or RC structure. In this research, a special spring viscous damper was developed and combined with the pre-stressed cable. These cables are then connected to each floor of the building through a device called deviator. This thing is deviator, which connects the cable to each floor. This figure shows the hysteretic curve of this viscous damper and cable plus viscous damper. As we can observe, the cable plus viscous damper has the less or approximately zero residual deformation. In this slide, we can see all the components of the viscous damper cable system. This is viscous damper, pre-stressed cables, deviator, and how it is attached to the structure. For viscous damper cable system, a special spring viscous damper was developed, which consists of a damper with a linear spring attached to it. The spring viscous damper is attached to the foundation or lower part of the structure and connected with the cables at the one end. This spring viscous damper is then moved to its center position by applying the pre-stress in the cable so that it can provide the recentering in both directions while keeping the cable stressed at all the times. This slide shows the cyclic loading test of the spring viscous damper. It's an analytical model and the hysteresis obtained from the experiment. This also shows the deviator, which is also attached to the structure, and its analytical model. In this slide, we can see the spring viscous damper attached to the structure at the bottom part, and the cables are going through the deviator and pre-stressed at the top. This is the shake cable test of El Centro earthquake with the bare frame without any retrofitting, and the similar structure is retrofitted with the spring viscous damper cable system. So to observe, we can see that there is a large shaking in the bare frame. the retrofitted structure, we can observe that the interstory drift ratio is less. In this slide, we can see the results of the shake table test. These displacement time histories of the two records scaled to the maximum considered earthquake, we can observe that the displacement of the retrofitted structure is significantly lower compared to the base structure. The other main advantage of the seismic retrofitting strategy is that it can reduce the acceleration on the other floors, as we can observe in these acceleration time histories. Finally, the maximum interstory drift ratio of the retrofitted structure is significantly low, which is 70% to 75% less than the bare frame. In the final part of this research, a seismic performance and life cycle cost analysis of a structure retrofitted with the viscous damper cable system and conventional viscous damper are compared. For this purpose, a 4-story RC structure is retrofitted with the viscous damper cable system and the conventional viscous damper. For this purpose, 32 viscous damper are used to achieve the performance level of limit state, immediate occupancy limit state or functional limit state, which corresponds to the 0.75% interstory drift ratio. And however, for the viscous damper cable system, only 12 viscous dampers are used. This slide shows the few time history analysis of the damper cable system and the conventional viscous damper and the bare frame. We can observe that for the case of the damper cable system, the residual deformation is least in every case. Using the incremental dynamic analysis for 22 earthquakes records, we obtain the fragility curve for 3 different limit states: immediate occupancy, life safety, and collapse prevention. And we can observe that the case with the spring viscous damper cable system is least in all the 3 limit states. The interesting point is that for the initial cost, the spring viscous damper is 40% less compared to the conventional viscous damper. And for the life cycle cost for the 50 years of earthquake, for a 50 years time period, the viscous damper cable system is 85% less compared to the bare frame, while the spring viscous damper cable system is approximately 26% less compared to the base structure. Hence, it is more effective than conventional viscous damper and the bare frame